Hi everyone, my name is Deanne Ryder and welcome to today's SEG webinar. I'm the webinar coordinator and I'll be moderating today's webinar. I'm going to give it a little bit more time while people are joining, but in the process, I just wanted to go over a few logistical items. We will have the conversation today is going to be listen only for participants. We invite you to submit a question using the Q&A button at the bottom of your screen. You can type your question in there and then we'll respond to them at the end of the presentation today. And then I will be sharing logistical comments or answering any questions on logistics in the chat box. So you can answer those or ask those of me there, and I'll be sharing information. And then, so that everyone knows, today's webinar is being recorded and an archive will be available following the event. If you've missed one of our previous webinars, I encourage you to go and look at the SEG website or our YouTube channel for archives of those presentations. And with that, I'd like to introduce Zhaoshan Chang with Colorado School of Mines and the SEG 2020 International Exchange Lecturer. The SEG Traveling Lecturers program was created to recognize excellent speakers who have made a significant contribution to the field of economic geology and to support their participation in events relevant to the minerals industry, as well as for SEG student chapter events. They serve as ambassadors for SEG. And then Zhaoshan will be presenting on skarns, zoning patterns, and controlling factors. Zhaoshan?
Yeah. Okay. Thanks, Deanne, for the introduction, and thanks to everyone for coming to the webinar. So today we're going to talk about skarns, zoning patterns, and controlling factors. Okay, so I guess you are here, you probably are very interested in skarns, so otherwise you probably won't come. But I would just spend a minute or two to say why we're talking about skarns. Skarns are important. In addition, you may notice many type of deposits like porphyry or VMS, etc. Epithermal, they have only 1 or 2 or 3 commodities for gold and copper and moly for porphyry, and only gold for epithermal deposits. But skarns, we can really have a lot of metals: gold, copper, tin, tungsten, lead, zinc, moly, iron, etc. And if one commodity price is down, the other commodity may be up. So you have this buffer. And geologically, it's also very common. And so this is a diagram showing in my database, I have about 1,630 skarn deposits. And those ones are all reported in the public literature. And if you have worked in the industry, you probably know that there are so many deposits haven't been reported in the public yet. So there's just skarns are just so common. Many places, as long as you have a little bit of intrusion and carbonate, and sometimes even you don't need carbonate and to make skarns. So it's very common. And in terms of the economic value of skarns, it's actually the major source of tungsten and tin. Those two metals, they depend on the years. Some years they are important, and currently they are not that high value. But if it ever comes back again, think about skarns, and these are the major source of tungsten and tin. Then base metal and gold, they are also significant resources of those metals in skarns. For example, this is the open pit of Antamina. That was in 2005, there were already about 3 billion tons of resources with both copper and zinc and silver. They also have moly, but the moly was going to the not being utilized at the moment. So very big deposit. And also sometimes you may have more than one type of mineralization in the Skarn district. Erzberg, Grasberg district, right now it's called a porphyry district, but again, depends on the year. Some years VMS has been very trending, and right now porphyry is very trending. So people call those deposited porphyry. But if you look at the resources reported, and this is the recent one, Carlin-like reported that in 2012, that's the Dixitable volume. And if you look at the resources, actually, there's more skarns than porphyry. It's about 60% of the copper and 55% of the gold actually are in the skarns, not in the porphyry. But still, this is still known as the largest copper gold porphyry in the world. This is one, Oktedi, that's another one in PNG, Papua New Guinea, both skarn and porphyry, kind of near in Mexico, Bingham, a big one, Utah, they have different proportions of skarn and porphyry. And the thing is, typically skarns are relatively high grade, and when you do your mining, you start with skarns as to get your cash flow. So they are high grade sweetener in porphyry deposits. So if we look at the overall system, skarn and related deposits, we may have skarns. We will have a skarn, and some of them are proximal, some of them are distal, and going towards the proximal side, and we can transition skarns to porphyry deposits. Many people are interested in porphyry deposits, only probably mostly heard about porphyry deposits, but there's also another possibility that you may actually get a greisen deposit. And those two are very different siting. And one is oxide siting, one is reduced siting, and depends on your siting, you will get different types of deposits on the proximal site. And if you go further away from the causative intrusion, we may have CRDs, that's carbonate replacement deposits. And those are typically zinc, lead, silver, and occasionally, or some unusual deposits like Uchu Chakwa, they also have hydrothermal manganese mineralization in those CRDs. And then further out, we can have Carlin type deposits, or if they have visible gold, that's no longer Carlin type, and people in Carlin say, oh, those are not Carlin. So we call it Carlin-like, but they are both replacement of carbonate, similar feature in terms of alteration. Okay, so we can have a very big system related to skarns. And today we're going to talk about zoning patterns, and the importance about zoning pattern is that it will help you to find out where you are in the whole system. And then after that, it helps you to vector towards other parts of the system, either inside towards porphyry and greisen, or outside towards CRD and Carlin type, Carlin-like deposits. And another function of this is to help determine the causative intrusion, because in porphyry deposits, skarn deposits, it's very typical to have multiple intrusions in the area. And which one is the causative intrusion? Sometimes, a lot of times, zoning probably is the only one reason to way to find out the causative intrusion. Many people use dating. That's unless your deposit is only about 1 million years or 2 million years old, you probably can use dating. Other than that, older than that, our dating technique is just doesn't have the resolution high enough to tell you which one is the causative intrusion. Be very careful. I saw people using dating to determine the relationship between mineralization and intrusion in arcane. And you think about that, your error, the uncertainty of dating is plus minus 10 million years. And a deposit formed only in probably 50,000 years. So there's no way you can use dating to determine the relationship. You have to use the geology, use zoning. Okay, and skarns are typically zoned. If we have a scenario, we have intrusion here, and we have calcareous wall rock here. And then typically in the intrusion along the edge and to some degree inside the intrusion, we can have inner skarns. Then we have a whole lot of exoskarns, massive exoskarns. Then going further out, and that's depends on what you have. If you have limestone, then you can have bleached marble, then go to marble, then go to limestone. And we say bleached marble because limestone a lot of times are gray color or dark gray to black color. And the bleached marble is just white. And then normal marble, it's recrystallized. You can see the grain size, but it's still gray in color. So that's that transition. And if you have not marble, not limestone, but calcareous shale, then this part you can have calcitic hornfels rather than marble. Or if you have your proselytes is alternating beds of limestone and shale, then you can get reaction skarns. And that's also in this part. Those are all metamorphic, mostly metamorphic skarns, part of the system. And in addition to those, and you can also have fluid escape structures, and those are little veins and can go far away into marble, even into limestone distal place. So those are the overall zoning pattern in skarns. And sometimes that's all good, but sometimes the massive skarn can be quite big, and you may have hundreds of meters, sometimes more than 1 kilometer of massive skarn. And this pattern, if you have that kind of scenario, you may still get lost. You say, I'm standing on the outcrop of skarn, but which direction should I go to find the causative intrusion, and which direction should I go to look for the distal signatures of or distal mineralizations of this system? So if you have that kind of question, then we do have other zoning patterns in the massive metasomatic skarn part. And those are typically, we can look at the garnet-Parkson ratio, and typically closer to the intrusion, there's more garnet, and away from the intrusion, getting closer to the marble front, where you have more Parkson. So the garnet-Parkson ratio has a decreasing trend outwards. Another one is garnet color. The garnet color change is typically fairly dramatic. And inside the intrusion or closer to the intrusion, we have dark red to red color. Then you go away to red brown color. Then you go further away, close to the marble. You start to have yellow garnet or greenish color garnet. So the lighter, the further away, and the lighter the color of the garnet becomes. So that's garnet color. Parkson color also changes from relatively light green color closer to the intrusion to darker green Parkson away from the intrusion. So these are all green color, different hints of green color. So it's not as dramatic as garnet. So those are the things actually you can just in the field, when you do logging, you can map in logging, and you can map out the zonation in the field without any other delay. And if you want to confirm and find more trend, or sometimes when those things are not that obvious, you can also do lab work, maybe simple lab work, microprobe, very routine technique, and you can check the manganese content in Parkson, and also in amphibole too. And typically the manganese content increase towards the distal part, toward the marble front. And when you are really getting close to the marble front, you even start to have manganese minerals, like rhodonite, permangite, etc. So those are pure manganese minerals, no longer just a little bit of manganese in those pyroxene or amphibole. So that's the general trend. Okay, so next, that's a summary, and then next we will look at some examples. So this is the copper skarn, and this is part of the Bingham system. Fark is just the northern northwest side of the Bingham porphyry. And this is Bill Atkinson did the work, and this is Larry Miner summarized the findings into a diagram. Basically, we have intrusion here, and then we may have different types of protoliths. We may have shale, and we may have sandstone, then we may have limestone. And obviously, the skarn mainly develop inside the limestone layer. And you can see we talk about garnet-pyroxene ratio. So closer to the intrusion, that's garnet much more than pyroxene. So the ratio is much higher. Then you go away, still more garnet than pyroxene, but the proportion of pyroxene has increased. You go further out, and that's garnet equals pyroxene. Then you go further out, that's pyroxene more than garnet. Yeah, so that's the trendy, the change of the trend. And when you go further out, sometimes yes, sometimes no, you may have a wollastonite dominant zone at the marble front. And in the wollastonite zone, wollastonite vasivonite, and with a little bit of garnet pyroxene, but still there's more pyroxene than garnet. The garnet color, closer to the intrusion, that's red-brown color, and then you go further out to brownish color, and you go further out to brownish to green color, and then to yellow-green color. And further out, it's green-yellow color. So you can see the very obvious change of the color. So that's a copper skarn, a relatively big one. It's another one, even a small one. This is called, actually, this is in Mexico, a prospect called Mexico. Sorry, this is in the Philippines, in the country of Philippines, but the prospect is called Mexico prospect. And it's fairly small, and you see this is 38.3, that's skarn and intrusion, and 54 meters, that's only 60 meters, so fairly narrow skarn. But you still see the clear change of garnet color. And this is the inside the coarse diorite causative intrusion, that's epithermal, and this red color, that's dark red color, that's the endoskarn part. And then you go out to the proximal skarn, fairly proximal to the intrusion, and you see that's red-brown color. And you go further out and become brown color. This is yellowish brown color, and you go further out, that's marble, residual marble, and that's the garnet, and those garnet are almost just yellow color. So you can see the color change of the garnet over the distance from the causative intrusion. So those are examples of copper skarns. And then another example, this is the zinc skarn, that's groundhog deposit in the United States. And the intrusion, this is a hypothesis out of a major intrusion, so a seal or a dike. And the intrusion itself is way, way to the left. So by the time of this tiny dike, the temperature is already low. Then still closer to the intrusion, we see this red pattern, and this red pattern is garnet more than pyroxene. And then further out to the green pattern is pyroxene much more than garnet. And then further out, and we have this purple color, and purple color is bastnäsite, rhodonite, and bastnäsite is the solid solution between rhodonite and wollastonite. So they are all manganese minerals. And so you can see the change of the garnet-pyroxene ratio, and also we mentioned the maximum Zhaoshanite, JO, that stands for Zhaoshanite. Zhaoshanite is the manganese end member of pyroxene. So maximum GO in pyroxene, that means how much is controlled by how much manganese in your pyroxene. So closer proximal is less than 25%, and you go in the middle part, and that's 25 to 50%. And the distal part, those pyroxenes will be more than 50% Zhaoshanite. And obviously further out, you will have manganese minerals like those sphagnumite and rhodonite. So the zoning pattern still occurs in this system, in the zinc system. Next, we're going to look at a gold system, and this example is called Fortitude in the United States. And again, a major intrusion, then some narrow dikes coming from this intrusion. And the garnet-pyroxene ratio here is 2:1, here is 3:1. So in general, closer to the intrusion, there is more garnet than pyroxene. Then you go further out, that's 1:3. So you have now more pyroxene than garnet. Then go to 1:5, and even more pyroxene, 1:20. That means your garnet is less than 5%. So it's dominated by pyroxene. So this garnet-pyroxene ratio holds up. And if we look at the Zhaoshanite, this time it's zinc skarn typically is distal, so they have more Zhaoshanite. And this gold skarn is not that distal. This is already close to the cutting intrusion. So there's not much manganese, but still it shows a subtle trend. So closer you see 0, 0, 0, so no manganese in the pyroxene. But when you go further, we start to have 4% Zhaoshanite, and if even further out, we have 6% Zhaoshanite. It's not much, but still shows a trend. Okay, so that's the trend. We have been talking about garnet-pyroxene ratio, garnet color, pyroxene color. We haven't shown much because it's relatively subtle. Then this one we mentioned at the marble front, you may have a wollastonite zone, may or may not. And this is a hand specimen just to show that little thing. So that's marble. Remember we mentioned dark marble. It's in the field. How do we know it's marble or limestone? My thumb rule is use my hand lens. If I can see grain size, I call it marble. If I can't see grain size, that's limestone. So this way you can keep consistent when you do mapping in the field. So this one is already recrystallized, but it's still dark, and it's dark marble. And then when you get too closer to the skarn, then you start to have bleached marble. The reason for that actually is because the dark marble, in the class, I will pass and ask you guys and until I get an answer, but we can't do that now. So I'll just tell you the answer. You can think about that, why the marble is dark or the limestone is dark color. It's because organic carbon. Marble limestone is formed in the ocean and is more or less some dead animals or dead plants in the ocean, and that's the organic carbon got into the limestone, and that's causing the dark color. Well, when you are closer to a hydrothermal fluid or higher temperature a geological body like an intrusion, and you're going to have higher temperature. You have temperature, you're going to cook your organic carbon. So basically your organic carbon gets heated up and becomes CO2. Then you release the CO2, you get rid of the organic carbon, and your marble becomes white. And because you have the dark, and the reason for the dark color has gone. And then we may or may not have a wollastonite and beautiful crystals, always radio aggregates, and then you go to the garnet-pyroxene, the massive skarn. So that's a small sample showing it can be a much larger scale, but it's easier to see with hand slicing. And we also talk about further out, after we leave the massive skarn part, the hydrothermal system doesn't stop at the end of the skarn or the marble front. And the hydrothermal system still continues further out. And at a small scale, and we call it fluid escape structures. So that's what it looked like. And this is massive garnet and pyroxene skarn. This is big Greisen in the Grasberg district in Indonesia. And so you go further out, you see those little green veins. And those veins can be green pyroxene, it can be green chloride, it depends. But you do show those veins coming off the massive skarn going into the marble. Another example, massive garnet skarn, and then you have narrow garnet veins coming off the massive body going into the white marble. So that's right at the contact. Then you go further out, then those green veins no longer available, this is actually also steel veins, but those are black veins, typically chloride or clay, mixture of chloride and clay. And if the rock is fresh, you may find very, very tiny grains of disseminated pyrite. So that's about 50 to 100 meters away from the massive skarn. And then if you go further out, that vein gets narrower and narrower, and eventually it's like stellar-like, curvy and very narrow veins. So that's in Grasberg district in Indonesia. Another example is Yaojialing in China. It's a zinc gold skarn, and you see the white marble. You see those curvy, very curvy, narrow veins, convoluted, and those like stellar-like, and those are actually fluid escape structures. It means something. We mentioned that, and if we have sometimes over the outcrop, you see those ones, and it looks like black veins in limestone or marble. It doesn't look much. And if you take the whole rock analysis of this one, it doesn't show really much anomaly. But if you crack open the vein, and you will see coatings of iron and manganese oxides of the veins, and you scrap this and send it to the lab, you may have very high manganese and silver anomaly. And those are all very distal signatures of skarn systems. They may not look much, but if you are keen and with a very well-trained eyes, and you can see those anomalies and follow up and find the skarns. So sometimes you go further out and you don't even have veins, and no more skarns, not much veins, but there's still systems, hydrothermal signatures, and they're just carbonate. So what do we do? And we can use the signatures in the carbonate, and we can look at the carbon and oxygen isotopes. And this is the example of El Mochito in Honduras. It's a zinc-lead skarn, and some of them occur, the skarn occur as parallel to the bedding, and that's mantles, and some of them cross-cutting the bedding, and that's mantles. Chimneys, the chimneys, and so mantles and chimneys. And if you look at the carbon oxygen signature, and this one is oxygen above and carbon below, and about 20 to 25 per mil oxygen signature, oxygen isotope combination, that's sedimentary signature. And if you see, this is relatively fresh sedimentary carbonate, and you go closer to the skarns, you see those ones 18, then 9.5, it goes lower number, that means there's hydrothermal signature. So it shows the lower values than the 20 to 25. That shows you the signature of hydrothermal fluid. And so we can use the carbon oxygen isotopes, and this one, if there's not a long veins, if we don't follow the structures, and the halo is 300 to 400 meters wide, and if we happen to have a fracture of fault, and following that fault, it can go up to 4 kilometers away from the causative intrusion, or not really causative intrusion. It's away from the skarn body, massive skarn body. And the causative intrusion of this one probably is still not found yet. It's still some distance away. So it can be really far away. The very cryptic signature we can detect use carbon oxygen signatures. Okay, so as a summary, if we have an intrusion, we have different types of proteolysis. Obviously, skarn will develop most favorably in limestone layer, and garnet-Parkinson ratio change, garnet color change, Parkinson color change, and that's the main thing, changes in the massive skarn. Then further out, we may have developed bleached marble, then we can have those blue escape structures going even further away. Then depends on if you have other type of proteolysis, you may have different scenarios. If you have calcareous siltstone and siltstone or shale, then you end up with a lot of calcilicate hornfels. And those ones are relatively fairly hard and impermeable. So it actually blocks fluid flow. It makes it difficult to form hydrothermal skarns. Those calcilicate hornfels, and those are metamorphic skarns. And you will see the width of massive skarn will be much narrower in this type of layer. And if you have skarns, you may have garnet-Parkinson veins cutting into those calcilicate hornfels like this. If no calcite in shale, then you have no hope to form any skarns. It's mostly just hornfels. If you have alternating bands of shale and limestone, sometimes only centimeter wide thick beds, and then you will form reaction skarns in the distal part. Then going further closer, you have bony skarn. The bedding is no longer that clear cut, but you still roughly see the bedding. Some layers are garnet dominant, some layers are Parkinson dominant. And you go further closer to the intrusion, then all those original sedimentary texture are obliterated and you don't see them anymore, and they become just massive skarn. Skarn along the edge as pervasive and more inward as veins of skarns. And I have a question asked even before we start. Skarn, can we have garnet-Parkinson veins in intrusion? Yes, it's very common. And a lot of them occur as veins, garnet-Parkinson veins inside the intrusion, no problem at all. Okay, so that's the general summary of the skarn donation. And by this time you may say, oh, Zhaoshan, you talk about this like so easy. Why, how come I don't see those patterns in my skarn, in my prospect? Yeah, we are talking about an ideal system. We start with the easy one. We start with the ideal system as the baseline. Then we look at the factors affecting the formation of skarns and affecting those zoning patterns. And we add in one or more, one communication at a time, and then we continue to increase our understanding of skarns. Okay, the factors affecting the formation of skarn, why my prospect is more complicated than this. That's because there are so many factors affecting the formation of skarns. The first one and the dominant one is the redox state gradient between magma and wall rock. So sometimes I see people say, oh, this is the oxide skarn, this is a reduced skarn. Well, it's not, sometimes it's not exactly. Okay, so what skarn you can get is not depends on purely by the wall rock, not purely by the intrusion or the magma. It's actually by the gradient, the redox gradient between the magma and the wall rock. Okay, we will look at some examples a little later on in the next slides. And then the next factor, the causative intrusion, obviously it will affect your skarn because everything all the volatiles and metals and come from the causative intrusion. So you will have impact from the causative, the features of the magma. And then the local ingredient is the wall rock. So the composition of the rock, the redox state of the wall rock, the permeability of the rock, wall rock, etc., will also have a big impact on your skarn feature. So we'll look at that detail too. Then the depth of formation will have impact. The distance from magma will have impact. And so we'll talk about this one by one. So that's the zoning pattern we have talked about. And you think, oh, this is nice. But this actually is, this pattern has the assumption. And the assumption of having this pattern is that your intrusion is the oxidizing intrusion and your wall rock is the reducing wall rock. Or that this, the reason, does this assumption, is this assumption valid? Well, especially for copper skarns, this is probably most time it's valid. Why it's valid? Well, limestone, we mentioned limestone typically it's marine sediments. There's dark color, black color. It tells us that it's organic carbon. So the organic carbon is carbon -4 status. So it's fairly a very good reducing agent. So the limestone is reducing because of the organic carbon. And the intrusion, we'll talk about more details later on for copper and moly, and the intrusion has to be oxidized. Otherwise, you won't have copper and moly. And so that's why we'll have this oxidizing intrusion and going to reducing wall rock. And we have a gradient going out, and that form this pattern. And the mechanism of this pattern is related to the ion. And because skarns have lots of iron, that's 20%. Without magnetite, the garnet and paraffin and chloride, it can go to 20 to 30% iron. So lots of iron, you need a lot of iron to form most of the skarns. So iron in nature, it can occur as 2+ or 3+. So then we look at the major species of garnet, grossular and andradite. And if we, that's the chemical formula of grossular, calcium, aluminum, and the chemical formula of andradite, calcium, iron. And the iron here is 3+. And for paraffin, we can have diopside, heidelbergite, and Zhaoshanite. And so they all have calcium, but the end member is different. Diopside is magnesium, and heidelbergite is iron, and Zhaoshanite is manganese. And our focus is iron. So the iron here in paraffin is 2+. So watch out for this. Paraffin is 2+, and garnet is 3+. Well, if you have an oxidized condition, most of your iron occurs at iron 3+. So you end up, you can't form paraffin with iron 3+. You have to form garnet. And when you go to closer to the marble, your reducing capacity is much stronger, and the fluid gets reduced, and your iron occurs as iron 2+. And in this case, you can only form paraffin. You can't form garnet anymore. So that's why the garnet-paraffin ratio changes high here and low closer to the marble front. And that's also the paraffin color change. The more iron you have, and the darker the color. And so when you are closer to the intrusion, there's less iron 2+, so it's lighter color. And you go to closer to the marble front, there's more iron 2+, and you get darker color in your paraffin. Okay, so that's why we have those patterns, and that's because the redox gradient. Well, nature is never the same, and we always have exceptions, and actually sometimes the exceptions can be more than we are aware of. So if we have an extreme situation that if we both the magma and the wall rock are reducing, what will we have in terms of skarns? well, if both of them are reducing, then the whole system is reducing. You have lots of iron 2+ and not much iron 3+. So what will happen? You probably end up with a lot of iron perishing. In that case, if you're trying to look for my garnet zone, I need to look for my garnet to know I'm closer to the intrusion. You may be disappointed, and then it's just the whole system is dominated by perishing. And this is the example, nickel plate gold scar in the Hadley district in Canada. And that's this color, the red color, that's the causative intrusion Toronto stock. And what's the feature of this one? And something you can use in the field is always, as an economic geologist, if you see an intrusion, you always pour out your magnet and test whether there's magnetite in your intrusion, because that tells you the redox state of your intrusion. And if you see black metallic mineral and has magnetism, then that's magnetite. If you still see that black metallic mineral but no magnetism, that's likely to be eumenite. And if you see eumenite and no magnetite, you are looking at a reduced intrusion. Okay, if you want to be more quantitative, you can send it to Acme or ALS and get the assay, and you use iron 3+ divided by the total iron. If this ratio is above 0.4, that's oxidizing. And if it is less than 0.4, we take it as reducing. It's an arbitrary number. And if we look at this one, 0.15, it's fairly reducing intrusion. And we have reducing intrusion and reduced wall rock, and what do we have? And perishing more than garnet. So look at the scale here, that's 1 kilometer. So that's 1 kilometer, 1.5 kilometers of perishing skarn. And the garnet right next to the intrusion, you still have a little bit of garnet, and that garnet is mostly grossular because the aluminum coming from the intrusion. And so overall, your system is dominated by perishing. And so watch out for this. The opposite extreme, and remember, is both the magma and the wall rocks are oxidizing. And in that case, what do you expect? Well, let's look at the example here. That's the massive skarn in the Philippines. The causative intrusion is direct porphyry, lots of magnetite, and so it's oxidizing intrusion. And the wall rock is special. It's no longer an original limestone. It's a marble conglomerate, and it looks like it's a conglomerate with fragments of white marble, and between the white marble, the matrix are clay minerals. And so maybe there was limestone, then there's regional metamorphism, you cook off all your organic carbon, you become white marble, and that white marble later on tumbled and brecciated and deposited into a valley and or river channel, and become a conglomerate. So by this time, the intrusion comes out, there's no longer organic carbon, so it's not reducing. So we have oxidizing magma and non-reducing wall rock. And what do we have? And that's what we got. So from the intrusion to the wall rock, you have already seen this. We talk about garnet color when we talk about these slides. And this time we're looking at garnet perishing ratio. And so what do we have? Mostly garnet, and green color is epithermal, so no perishing. And this is mostly garnet. This is perishing, a little bit of greenish, and that's perishing. So 9 to 1% proportion of garnet perishing. And here, mostly garnet, very little amount of perishing. And mostly garnet, mostly garnet. So if you have this kind of wall rock and wall rock and intrusion, you try to look for the distal part, and I want to look for, I need to find my perishing, and you won't. And you already got into garnet, and you're already at the marble front because of the redox gradient between the magma and wall rock, and they are all oxide. Okay, so that's one of the major things controlling that. Okay, next we're going to look at the magmatic signature control volatiles. if we have fluorine, what will happen? And this is unusual deposit skarn in called Empire copper zinc skarn in the United States in Idaho. And one thing you notice is a lot of indoskarn. So you see the indoskarn occur as veins. So these are granite porphyry, big phenocrysts of K-spar, big phenocrysts of quartz. And it's definitely an intrusion then cut across by veins of garnet. And when the veins coalesce, when you have multiple veins and coalesce, and you become more and more massive, and eventually you just have massive garnet piercing with small patches of residual intrusion, altered intrusion. So lots of indoskarn and much more than exoskarn. This is very unusual because normally we have lots of exoskarn and not much indoskarn. And the reason is that limestone is much easier to dissolve, where our magmatic hydrothermal fluid comes out with a little bit of weakly acidic with hydrochloric acid, a bit of sulfuric acid. So they are weakly acidic. Well, when you have acid and limestone encounter each other, what happens? Well, they bubbles and dissolves lots of limestone. It gives the supply of calcium, it gives the space to form skarns. So you typically form massive, large amount of exoskarns. In the skarn, you have silicates, and silicates, it's very, very difficult to dissolve. If you go to a lab or you want to dissolve silicates and you say, oh, I put in aqua regia, very strong acid, nitric acid, hydrochloric acid, and sulfuric acid. Does it dissolve silicates? No, it doesn't work very much. You have to add hydrofluoric acid. So it's very difficult to exoskarn than indoskarn. But here you have more indoskarn than exoskarn. Another unusual feature is here we have proximal zinc mineralization. The zinc mineralization even occurs inside the indoskarn. And the general situation is copper moly is proximal, zinc lead is distal, manganese distal, and this is against the normal trend. So the reason for that is we have high fluorine in the system, in both the magma and also in the skarn systems. We have good indications of fluorine. I won't read out those later, the numbers, but it's the idea is there's much more higher fluorine than usual situation. Well, if you have high fluorine, the high fluorine will greatly facilitate the dissolution of the silicates, then give you the space. You can have those veins and all those pervasive alterations of the igneous rock and to form the indoskarn. Another feature is fluorine can decrease the solidus temperature of the magma. So normally granitic magma, no water, you probably have looking at solidus temperature of 800 degrees C. If you have water, it gets down to maybe 650 degrees C, 600. If you add more fluorine, and that again further destroys the chemical bond between oxygen and silicon, and I can reduce that down to even 500 degrees C. So the reason zinc lead is further out and copper is more proximal is their solubility. And solubility of zinc is much higher in solution. And so they can stay in the fluid at relatively higher temperature. And then until you have lower temperature, then it doesn't come out. So they need the lower temperature to come out. And that's why zinc is distal. And now we start with a source already low temperature. So the fluid doesn't need to transport for long distance to be away from that intrusion to be low enough to deposit zinc. And that's why we have zinc mineralization close to the intrusion. So that's the function of fluorine on the formation of skarns and mineralization. You say, oh, that's good. But fluorine analysis, and you have to send it to the lab, and you have additional costs to analyze fluorine. So do we have anything in the field we can use to indicate high fluorine? And yes, and we actually found some interesting things. you look at the quartz phenocryst, and the blow up of the quartz phenocryst, and you see it's very much vermicular and very much corroded and very even inside the quartz crystals. And the outline of that quartz is no longer euhedral. Typically, you should have euhedral phenocryst, but it's no longer euhedral. So that's caused by fluorine. The fluorine also dissolves silica quartz way inside. So in the field, if you see this type of quartz phenocryst, think about the possibility of high fluorine. Then you can think about the consequences of having high fluorine, which is a lot of endoskarn and proximal mineralization of low temperature metals. Okay, so that's intrusion impact, and the combination of the intrusion and the redox intrusion, it's also a strong impact, and we'll talk about that in the next part of the donation. So effects of wall rock and the combination of the wall rock. Obviously, if you have limestone, you form calcic skarns, and if you have dolomite, you have magnesium skarns, and they look dramatically different. That's one effect. Second effect is redox of the wall rock. So we have the same intrusion if we have reduced wall rock versus oxidized wall rock. And reduced wall rock is carbonaceous, looks black, easy. And oxidized white color or even red color, that means you have hematite and iron 3+. And so that's oxidized. And during the early metamorphic stage, you will form calcitic chlorophyls, and the amount of calcium chlorophyls will be dramatically different. If there is reduced wall rock, your calcium chlorophyls will be much narrower and is dominated by pyroxene, no garnet. And further out, you may have biotite chlorophyls. And if you have a oxidized wall rock, your calcium chlorophyls can be much wider, and you also have a much wide garnet dominant calcium chlorophyll closer to the intrusion. Then you go out to pyroxene chlorophyls, and that's this stage. When you have the metasomatic skarn stage, you have massive garnet pyroxene. Again, you still have this similar effect. The skarns are narrower in the reduced wall rock, and the inside the garnet is less, the pyroxene is more, like we talked about just before. And if it is oxide intrusion, your overall width of the skarn will be wider, and also you will have wider garnet zone than pyroxene zone. Again, why is that? Why we have this kind of scenario? And again, that's related to organic carbon. Remember, the formation of skarns needs to have a reaction with the limestone or the limestone or the marble. And a simple one, the initial reaction is limestone, calcite, add. When you have the aqueous fluid bring in your silica, they form wollastonite. Then you have to release what? Release CO2. And see, the formation of the skarn needs to release CO2. But when you have reduced wall rock, you already have lots of organic carbon in the system. And when you when you heat it up, you already generate lots of CO2. So organic carbon, I should say organic, it should be CH4, or sometimes neutral carbon plus CO2, then you generate lots of CO2. So before you're forming this, you already have lots of CO2 in your system. That means you already have lots of this in your system. So this reaction will be slowed or even suppressed or even stopped. So because of so much CO2 in your system already. So that's why if you have a reduced wall rock, both your calcitic chlorophyls and your massive hydrothermal skarns will be narrower compared with the oxide. Okay, and next is other features of the wall rock. Sometimes you have the scenario like in in Peru, Antamina, Uchuchacua, those areas, you have very thick beds of carbonate. And, but the mineralization on skarn only occurs in certain beds. It doesn't occur in all the limestones. And so that's related to the proportion, the properties of the wall rock, the porosity and the accommodation. Accommodation means that whether you have pure limestone or impure limestone. If you have clay mineral, you during the metamorphic stage, thermal metamorphic stage, you generate reaction skarn or those minerals, and actually it generates secondary permeability, and that helps with later on the hydrothermal skarn formation. If you don't have that, you just have pure limestone, like the chemical precipitation of limestone, they are interlocking calcite. They have very low permeability. And so it's actually not easy to form skarn because you don't have the fluid flow. If you have another scenario, if you have lots of fossils, and or you can have clastic limestone, fragments of limestone forming still a limestone in the storm sedimentary environment. And in that case, you can have higher permeability and you have more skarns. So both the accommodation, porosity, and permeability have a big impact. And follow on this, we mentioned carbon oxygen isotopes can show us the signature, but again, sometimes like here, you can be up to 4 kilometers away along faults or 300, 400 meters away from the skarn. Another scenario, this is in Queensland, in Australia, Chillagoe district, and this is the drill hole garnet magnetized skarn. That drill hole meters, 340 meters, 360 meters, 380 meters, 780 meters. So you see, this is the skarn, so its oxygen isotopes is low, and 20 to 25, that's the sedimentary carbonate oxygen signature. And the halo, how wide is the halo? The halo is 740 to 760. So that's only about 20 meters wide. So here, that's 400 meters wide, and here there's only 20 meters wide. Why is that? And our hypothesis is it's actually the permeability of the limestone are different. And here, this is interlocking calcite in the limestone. You have really low permeability. So your fluid just is not flowing very much. Okay, so that's one. Another part, the geometry of limestone is sometimes people get confused. If you have limestone, shale, siltstone, and only a thin bed of limestone, you're going to end up with the strut bond shape of your limestone. And because there's only, the favorable layer is only narrow, a thin layer. And closer to the intrusion, you have massive replacement. Away from the intrusion, you're going to have replacement relatively narrow and occur along the boundary between those layers. And that's very typical. And some people say, oh, this is strata bond, it must be SEDEX or thin sedimentary or sedimentary. Watch out, this is still related to magma. Okay, we'll talk about this. And depths of formation. Okay, depths of formation, we can have, that's related to the ambient temperature and permeability, because shallow position, 2 kilometers versus 10 kilometers, your ambient temperature will be different. Think about thermal gradient, 30 degrees C per kilometer, and here, this is only 60 degrees C. And 10 kilometer steps, you are already 300 degrees C. The temperature is much higher. The temperature is higher, therefore the metamorphism will be, thermal metamorphism is much easier at depth. So your thermal metamorphic aureole will be much wider at deeper position. And here maybe only a few hundred meters or less than 100 meters, and here you can be kilometers wide thermal metamorphic aureole. And second, it affects your permeability of your wall rock. And if you have high temperature, high pressure with your limestone, it deforms and doesn't break. And that means your fluid will not be able to travel away from the intrusion. And so it will be confined around the intrusion. So you will have only a narrow skarn. Shallower place, you have lots of lower temperature and brittle deformation, lots of fractures, and the fluid can flow further away from the intrusion. You have lots of skarns. The skarn zone will be much wider at a shallow place. And the third effect is the retrograde alteration. Retrograde alteration at lower temperature is much easier to have retrograde alteration, but here your temperature cannot be lower than 300 degrees because that's the depth, that's ambient temperature. So the amount of retrograde alteration will be much stronger at shallower place. So we can look at some examples. Tungsten skarn as an example of deep skarn, and this is in California and next to the Sierra Nevada batteries. So that's a skarn intrusion already. That's 1 kilometer, so that's already several kilometers, but the batteries is much bigger. And if you look at the mapping around here, what do we have? Biotite, sillimanite, almandine, chlorite, and andalusite, etc. They are not skarns. What are those? Those are thermometamorphic halos. So that thermometamorphic halo is 1 kilometer, so 1 kilometer, 2 kilometer, 3 kilometer, several kilometers wide. So that's deep skarn has wide metamorphic halo. How about the skarns? Where's the skarn? Well, the skarn is here. So that's the intrusion here, limestone here, now changed to marble, and the skarn is just around here. And that's a person sitting here at the scale bar. Your skarn is only 1 meter, 2 meters wide, very narrow. And so very large metamorphic aureole, but very narrow skarns. How about a shallow intrusion? Well, if we use the copper skarn as the example, shallow intrusion, that's a intrusion 1 kilometer, so about 1.5 kilometers wide. It's a small stock. And this is the thermometamorphic aureole, and 1 kilometer, and this is only about, let's say, 500 meters of thermometamorphic aureole. Compared with that 4 kilometers, it's much narrower. How about the skarn itself? Well, the skarn 1 kilometer, and as you get here, the skarn is at least 200, 300 meters. And if you go here, that's almost 800 meters of skarn. So the skarn is much wider and the thermometamorphic aureole is narrower. And the third effect, remember, is the amount of retrograde alteration. And this one, that's the causative intrusion, and this is all black. And that's because the chloride overprint of the prograde skarn. So very strong retrograde alteration. Okay, I see we are late. I need to speed up. So next, we're going to look at the metal association and the metal zonation. So far we look at the zoning patterns in the alteration, and the metals also have zonations. So we are using examples of skarns in China to do this. And the reason for that is China used to be planned economy. So they calculate the estimate resources of all the metals, no matter whether it's economic or not. So it sounds silly, but now it actually gives us some advantage when we try to look at the metal associations. So that's 386 skarns in China. That's we just published the review last year in Economic Geology, Society of Economic SEG special publication. And so that's about the skarns, 386. So we have lots of data here. Let's look at the metal association. First, we look at moly, gold, and tin. And together, there's 162 skarns plotted on this diagram. And you will notice most of them are just plotted at the end member. So that means they don't have associations. They don't occur together. Between gold and moly, there's only 9. Have non-dip scars have both gold and moly, and as byproducts. Between moly and tin, there's only 4 scars have both moly and tin. And between gold and tin, there's only 2 scars have both metals, and the gold is only very small, a few tons. So it shows no association between these metals. So why we don't have association between these metals, and that's related to redox state of the causative intrusion and also the fractionation of the causative intrusion. There are 2 factors being considered. And the redox state, and that's Larry Manner's compilation, iron 3+ over total iron, the overall average is 0.4. So that's why we call it 0.4, above 0.4, we take it as oxides, and below 0.4, we take it as reduced. And you will notice that copper and moly, they are related to oxide intrusion. Iron, some of them oxide intrusion, some of them not so oxide, you still can get iron. So it's closer to the borderline. The opposite is gold only scar and tin scar. So watch out, gold scars, some of them are gold only, some of them are copper gold. Copper gold scars follow the feature of copper scar. Gold only scar is reduced and tin scar is reduced. Tungsten scar can be related to both oxide and reduced intrusions. The one related to oxide intrusion, you have copper and moly association, and the one related to reduced intrusion, you have tungsten and tin association. So they have different association, they have related to different intrusions. Zinc at that time in 1995, the zinc was most of the intrusion, no one intrusion is still oxides. But nowadays we have many more because the zinc, a lot of them are distal, so it's difficult to find the causative intrusion. But nowadays we know much more zinc with causative intrusion being found. And it turns out there's zinc also related to reduced intrusion. And so zinc, it can be oxide, can be reduced. So this part, watch out, is no longer valid. So you may ask why tin scar is related to reduced intrusion and moly is related to oxidized intrusion. And that's related to the behavior in the magma. So if tin occurs as 4+, then it substitutes for titanium 4+ and iron 3+. Then those ones, the tin can go into biotite or hornblende or titanite, eumenite, and magnetite. And so the tin actually is brought down into the bottom of the magma chamber, and they get dispersed. You don't get tin in the residual melt because the tin has been brought down by those magmatic minerals. And to get your concentration of tin, you really need to have a reduced situation, reduced magma, so tin occurs as 2+. If tin occurs at 2+, then they don't go into the magmatic mineral lattice, and so they get concentrated in the residual melt. So that's why tin is related to reduced intrusion. And moly is the opposite scenario. In nature, moly can have 4+ and 6+. If you have a reduced intrusion, then moly has 4+ and substitute for tungsten. So it gets dispersed. And to make a moly deposit, you need the oxide intrusion. So the moly is 6+ and get concentrated into the residual melt. So that's copper and tin, the opposite. So that's why they don't occur together. Gold and tin doesn't occur together. That's because they are related to magma with different fractionation. Tin is always related to very high silica, high felsic magma, silica content 74, 73%. And gold only scar typically relatively more primitive magma, not really primitive, but quartz diorite, dacite porphyry, granite diorite, that kind of accommodation. It's relatively low silica content. So that's the scenario. And there are other people using different factors to to talk about redox and fractionation. This is Phil Blaven from Australia using rubidium over strontium ratio to express the fractionation and using iron 3+ over iron 2+ ratio to talk about the redox, but the idea is the same. Also, he got the same conclusion from mostly the Queensland, Australia deposits. Again, moly, oxides, tin, oxides, they are all related to fractionated magma. And the copper is oxidized, but relatively less fractionated. It doesn't have gold. The gold on the skarn will be around this place. So that's why moly, copper, and moly, gold, and tin don't occur together. How about copper and tungsten and tin? So again, there's not really much association. So tungsten and copper is slightly better, but tungsten and copper and tin, there's 13 out of 184 skarns have those associations, so not much. And one of the big surprise is tungsten, tin, tungsten. We always talk about tungsten, tin, but they actually don't occur together very much. So only 10 skarns out of this 184 has both tungsten and tin. They're either tungsten dominant or tin dominant. So really only 2 have similar amount. So that's a big surprise. And the reason, again, that's probably related to the redox. Tungsten, the fractionation of the magma, tungsten is moderate fractionation to high fractionation, but tin is always highly fractionated. And the redox and significant amount of tungsten skarns are related to oxide intrusion. In that case, they won't be together with it. Worldwide, actually, Newbury 1998 already noticed those some things. That's the classic tin tungsten skarn, typically not really much tin, and the reduced tungsten skarn and have low moly, and that's because we talk about the redox. Next is copper, gold, and moly, and this is the 3 metals in porphyry deposits, and the trend in skarn deposits is very similar to porphyry deposits. So copper, gold, lots of association. Copper, moly, lots of association, but moly and gold, very rare, no association. We talk about that. And the redox, copper and moly, both are related to really oxidized magma, but in detail, there's slightly difference. So this is our paper in 2019 using the zircon trace elements, and those yellow squares, those are porphyry copper, and the Korean ones are porphyry moly plus skarn moly. And you can see the porphyry copper is relatively has higher redox state than the moly. Okay, so copper has even higher redox than moly. So you probably have noticed that people use zircon to talk about magma fertility. You say high serum 4 over serum 3 ratio, you have fertile, have more copper gold. And people will say, oh, if you have low ratios, it's not fertile. Watch out for this. They may not be fertile for copper gold or moly, but they may be fertile for tungsten and tin. So with reduced intrusion, you just switch the metal from copper moly and to tungsten and moly, then to tungsten tin, then to tin. So watch out for this. Another one is tungsten moly. They really have very strong correlation, and that's because both of them can be related to oxide magma, both of them can be related to fractionated magma, and so that's why we have lots of fractionation. Zinc lead is special. Zinc lead in China is, some of them you see zinc lead associated with iron, and that's more oxidized, and zinc lead associated with moly, that's also oxide. And so zinc lead can be associated with oxidized magma And also zinc lead can also have association with tin. That's reduced magma. So zinc lead can be related to both reduced and oxidized. And in fact, actually there's more. That's the 10 largest tin skarn, zinc lead skarn in China. And 3 of them are as subordinate metal in tin skarns. The most dominant metal is tin. And then there's zinc lead is actually not to say byproduct, but it's less important than tin. So the top 3 zinc lead skarns are actually related to tin. And 1 is related to gold, and the others are independent zinc lead skarns. So that's zinc lead can be related to both oxide and reduced. Another one is iron, and I bring out iron because iron actually, remember, to form skarns, you really need to have a lot of iron to just form garnet pyroxene. If we have additional iron, we'll form magnetite or hematite and form mineralization. And iron actually have a moderate association with copper, gold, moly, zinc, lead, and also have weak association with tungsten and tin. That's the tin, not in the extreme reduced scenario. If it is not so reduced, you can still have magnetite mineralization. So we can have lots of magnetite in skarns. In copper skarns, a lot of them, volumely, you look at them, there's much more magnetite than sulfite. And so the lesson here is to say not to confuse this with IOCG deposit. Some people just look at it, oh, there's a magnetite and the copper goes, or copper or gold, so it must be IOCG. So not necessarily. You have to look out and look at the geology rather than just look at the metal. Okay, so based on that, we can have metal association of 4 sets. If it is oxides and moderate to strong fractionation, we have moly, tungsten, copper, zinc, lead. If it is still oxide but weakly fractionation, and then we have iron, start to have more iron, and no moly but more iron, and we can have more gold, not moly. And zinc lead is here all the time. Reduced intrusion, strong fractionation, we will have tin at the more closer to the intrusion, zinc lead. Again, further out. And reduced intrusion to moderate sites of association, depends on the magma. Metal donation, zinc lead being distal is well known, but a lot of time people are thinking, oh, I have zinc lead, I trace it back to the intrusion, I should have a copper. Watch out for this. You may not have a copper, you may get a zinc, you may get a tin skarn. So watch out for this. And that's the example in China, EGRU deposit. 3 million tons of tin. It's huge, huge, giant deposit. And you go out to zinc lead. Watch out also, zinc lead being distal is well known, but the accumulation in the Chinese skarn turns out there are also distal mineralization of other metals. And there's tungsten skarn, this is one, this is tungsten mineralization, this distal intrusion hasn't been found. It occurs at the boundary between limestone and shale. Another example, this is Zhuxi, this is the largest tungsten deposit. It's 2.7 million tons of tungsten. This is huge. And you see closer to the intrusion, deeper part, and that's a lot of tungsten. You go further out and you start to have the green. The red color is tungsten and the green is copper. So you can also have a distal part, distal mineralization of copper. Other metals can occur in distal location. Tin can occur at distal location. Moly can also at distal location. Gold everywhere. So it can be proximal, can be distal. So watch out. You may have distal part, distal mineralization of those metals, not only zinc and lead. Now, if we put everything together, that's the accumulation. I don't expect you to remember this or see this. There's lots of deposits get compelled. And the conclusion of the zoning pattern is, again, based on the association. We have 4 sets of zoning patterns, not only one, okay? 4 sets of zoning patterns. Magma reduced and strong fractionation. In the intrusion, we'll have greisen type tin plus minus tungsten. Then proximal skarn, we have zinc plus minus copper plus minus iron. Then distal, we can have distal tin veins, and then far distal zinc lead veins. So that's if we have that kind of intrusion. If we have oxide intrusion, weakly to moderately fractionated, then in the intrusion, we will have porphyry and or inner skarn, moly and or copper. And proximal skarn, copper, iron, and plus minus gold and moly. And distal, we can have distal copper and far distal zinc lead plus minus gold. So that's that pattern. Oxides and strongly oxides fractionated. In the intrusion, we can have porphyry moly or greisen tin, tungsten. So moly or tungsten. And then proximal, we can have moly and or tungsten. And then distal, we have distal moly or distal tungsten, plus minus copper. Reduced, not in China, but in other part of the world, closer in the intrusion. In the intrusion itself, it's not much. But proximal skarn, we can have gold, like nickel plate in Canada, we saw the example. And the distal part, in China, we have the zinc lead gold skarn in Caijiaying. And the causative part of that skarn hadn't been found. And so we can have this kind of zoning pattern. You will notice that gold can be proximal or distal. It can be related to oxide magma or reduced magma. Gold is just everywhere. There's no specific location for gold. You can find gold anywhere. So the compilation, if you want to look at the details, and that's in this book, Mineral Deposits China SEG Special Publication number 22. And you can talk with Deanne to order this or go to the website, order this. So the final remarks is that in terms of metal zoning, there's no one metal zoning can fit all the skarns. You have to watch out. If you are always only thinking about zinc lead going to copper, think again that you may have different zoning patterns. And there are many examples of continuous transition from distal to proximal, up to 4.5 kilometers. We're not talking about the zinc skarn that are still isolated and you don't see the causative intrusion. We're talking about the ones are continuously transitioning from distal zinc to proximal, either copper or moly or to zinc, to tin. You probably can now have much more confidence that distal zinc lead will have a proximal mineralization somewhere. And you should be confident that you should continue to look around for that proximal mineralization. And it turns out the biggest skarns, they all have all the parts discovered. So from all the way to inside into the intrusion, proximal skarn, CRT, or even distal to the Carlin type deposits. If you find all those parts of the system, you will end up with the big deposits. Other things, okay, we can skip other things. At the last, I'd like to take just 30 seconds to advertise. We have a professional master's degree in exploration at the Colorado School of Mines. It's focused on mineral exploration, coursework only, and no thesis, and you don't need to take GRE test. And 10 courses and finish 30 credits. And if you really are keen about finishing, you can finish this in 2 semesters. And that's about 9 months, and you can get a degree. And it's mostly for industry career. And that's the website for the more information. Okay, thank you. I'm sorry, I'm way over time. But I will still continue. If you want to stay here. I'll continue to take questions.
Great, thanks, Zhaoshan. We do have quite a few questions that have been submitted, and just a reminder to all of the attendees, if you have a question, please submit it in the Q&A box, and we'll get to as many as possible. And one question, just taking a step back, what would a modern skarn system look like at the surface? And are there any volcanoes where you think this process is occurring today? And what would it look like with all of the CO2 in the groundwater system?
Oh, that's a lot of questions, actually.
I know.
In modern system, you have to watch out in terms of, you're talking about volcanic rocks. I think you're thinking about the erosion and preservation of deposits. When you see the skarn on the surface, that related volcanic rocks have already eroded away. And you have to think about the up and erosion rate. And in modern active zone, it's typically can get 3 or even 4 millimeter a year. And you think about that, 3 millimeter a year, that's how many kilometers a million year. So that means if we continuously to have that uplift in 1 million years, you're going to erode 3 kilometers of covered rock. So by the time you see your skarn and the causative intrusion, the directly related, well, I should take back, if you have a skarn form, that intrusion will not have a equivalent volcanic rocks. You think about that. If you have a volcanic eruption, you will lose all your volatiles, and you won't have your metals being preserved and to form a deposit. And it's either you have a deposit or you have an eruption, and you can't have both. And following on from the uplift and erosion is that you can have the same magmatic tectono-magmatic event, and you may have volcanic rocks of similar composition in that event. And typically that event in South America, it typically lasts for 5 to 10 years. You can't have both at the same time. Okay, well, the second question is CO2 content in the groundwater. Again, depends on the formation of the skarn, the depths, the formation depths. If you have a very deep skarn, then typically the skarn is narrow and small, and you have higher pressure, then you can have CO2 in the water. By that time, it's no longer groundwater because groundwater can't penetrate to that depth. And if you have a shallow intrusion, the pressure is low, and the CO2 solubility in water is very low in shallow water. And for copper, typically shallow skarns like copper and moly, and you don't expect to see much CO2 in the water.
Great.
And watch out for tungsten. Tungsten, traditionally, if you look at previous review papers, and tungsten is typically regarded as a related to deep intrusions. But it turns out China has much bigger tungsten stars, and they are related to fairly shallow intrusions. And it's probably the previous review are mostly based on examples in America, Canada, Alaska, a relatively deeper part, and so they are small and related to deep intrusions. And now considering other parts of the world, and tungsten probably are not only limited to deep intrusion, they can be related to small intrusions. Actually, if you want to find big tungsten skarns, you need to go to shallow intrusions.
Great, thanks. We have some questions from early on in the presentation. So some of them might have been answered, but I think it's good to give a little extra detail just in case. So what's the typical distance between intrusion and bleached marble?
And that's again related to the depths of formation. If it is shallow, and that's only probably a few hundred meters. And if you have a deep intrusion, then it can be much wider, and it can be kilometers.
And then
Watch out.
is there a typical zonation of high organic carbon content in marbles and more of a distal texture, or is it present throughout?
That's the organic carbon content is a sedimentary feature. It's not related to skarn. So that's already there when the limestone formed. So it can be anything. In Antamina, you will see the big beds of white and black. They are alternating bands. That's another scenario. And so you can have oxidized intrusion, oxidized limestone and reduced limestone alternating bands. And you will probably, with that kind of limestone, you will probably end up with lots of tiny skarns. And the white limestone goes to garnet, and the black limestone goes to pyroxene.
Great, thank you. What would be the main geological difference between a skarn and an IOCG system from a fieldwork perspective?
It's mostly the ground minerals. So IOCG is only talking about metallic minerals and mineralization. So some people see magnetite and chalcopyrite, and they call it IOCG. The main thing, actually, you should look at the ground minerals. In skarns, you will see lots of garnet pyroxene. And in some places, the garnet pyroxene may be retrograded to lots of amphibole and chloride. And if it is magnesium skarn, you will end up with lots of serpentine and sometimes phlogopite. And those are the typical alteration minerals, the ground minerals for skarn systems. And the traditional IOCG deposits in Australia, Southern Australia, Olympic Dam, that's where the term came from, or to the northern part of Australia, Ernest Henry, that's another typical IOCG deposits. And those alteration is typically there's a, the first order feature is breccia. It's very strong brecciation. And the class have plastic alteration. They're red color and plastic alteration with hematite dusting, and so it makes it red. And that's the typical alteration. They don't have garnet pyroxene, or chloride in their system.
So Zhaoshan, I just wanted to be aware we are running a little longer, but I assumed you were fine with answering questions for...
Yeah, I'm happy to answer question until 1 o'clock or 1:10. It depends on how many questions or how many people are still interested in those topics.
Okay, great. So I'll continue asking some of these questions, but just as a reminder for anyone who needs to switch to something else, we will archive the entire presentations, including these, the Q&A session now, and so you can reference it afterwards. And so the next question was, do we expect skarn deposits to behave in a similar way under different geological conditions or tectonic events?
This question is a bit vague. I'll answer according to my understanding.
Okay.
So watch out, we didn't have time to talk about skarns can be metamorphic and can be hydrothermal. And the metamorphic, they're pure metamorphic ones, they're metamorphic hydrothermal ones. The metamorphic hydrothermal ones will be similar to organic gold system. And in that case, the metamorphic ones, the zoning pattern doesn't apply to those. And magmatic hydrothermal ones, it's not much, there's very rare, but you do occur, like some of the tungsten skarns. The mineralization in metamorphic hydrothermal skarns, the mineralization is only limited to the tungsten and maybe gold in some cases. And they are rare. And in that case, metamorphic hydrothermal environment like organic, it's typically reduced because the fluid came out of the squeezing of the sediments, and the sediments, lots of them are black shale, black siltstone. And again, because organic carbon, you have lots of reduced environment. And you probably would expect to see more granular than hydrobagite, than the andradite in terms of garnet. And so we have I have a PhD student work on the watershed skarn in North Queensland, and that's the case. And so that's, then hydrothermal ones mostly is like that. But some of the very old ones, if it is in a Proterozoic terrain, and some other places, like in Australia, there are a few of them, the garnet pyroxene, they are subcaustic. They are not garnet pyroxene. I mean, not the andradite granular series. They can be very rich in almandine combination and spacetine. So manganese and reduced iron kind of scenario. So it's just not many cases of those. We're still trying to summarize their feature, but it's just not so much of those deposits. Other than that, typically skarns, most of them are having the zoning pattern like what I talked about.
Is there a significance of cobalt or silver associated with copper gold magnetite skarns?
Cobalt, we don't really know much about that. There's not many cases of those cobalt. One deposit with higher cobalt is the Altokic deposit in Chile, and it's a zinc-lead skarn. And locally, there's cobaltite, and there's no causative intrusion being found yet, and it still has cobalt. That's one case. In China, there's some of the a few deposits has cobalt together in iron skarns, and one of the things is that cobalt geochemically is related to mafic rocks, and if you have a skarn replacing mafic rocks, so that's another topic, but just be aware that skarns do not necessarily replace limestone. You can have skarns replacing mafic rocks, and either gabbro or basalt. In that case, if that gabbro or basalt has higher cobalt, you can have higher cobalt in the skarn too.
So for the fluid escape structures, are they typically random, or is there some sort of preferential orientation?
We haven't really done detailed work in terms of their structural controls. If their structures, definitely the larger veins will follow structures, but the tiny veins, because it's so convoluted, I doubt there will be structural controls. There looks like stellarite. Yeah, kind of, you have to have a fracture to do that, but that fracture will be probably many orders less. It won't be your first order fracture, it won't be a second order, it won't be a third, it probably will be fourth or fifth. By that time, whether it's a preferred orientation, it's uncertain. I just don't have, I haven't worked on too much on those yet.
Another question on what you've encountered so far. Have you ever encountered an anhydrite and proximal garnet in a rich, proximal garnet rich skarn?
I have seen anhydrite in a magnesium skarn. It's iron. I think there's another one, actually, iron skarn in China. It's fairly deep and also replacing anesthetic volcanic rocks and also intrusions. And there are lots of anhydrite. The name just slipped out of mind, but it's a big one in southern China, in Anhui province, and low grade, lots of anhydrite. Yes.
A question again earlier on in your presentation. What was the reason for the color change in the garnet?
That's a good question. We're working on that. It's empirical. It's actually among all the zoning patterns, it's the strongest zoning pattern. You go everywhere, every skarn I go to, I see that the color change. But the reason we have been tested the major combination. The major combination, there's people talk about iron content or titanium content. No, tested. It's not related to iron. It's not related to titanium. We did trace elements at a small, the Mexico prospect I showed you in the slides. It's the only element that actually shows zonation is tin. It's a weird situation, and we are going to do more trace element analysis and try to figure it out.
How would you interpret, from a zonation perspective, the calcite quartz sulfide leakage structures with the copper, arsenic, moly, and the bleached limestone?
Yeah, and when you go out, that's actually, if we have the zoning pattern, this lecture we didn't talk about the pyrogenesis of skarns. Typically, the prograde is garnet pyroxene. And if you go away and away, the temperature eventually is lower enough that you won't have garnet pyroxene forming because the temperature is so low. And by that time, you start to have carbonates. And you probably start with, there are several deposits, it was lots of siderite, it's the iron carbonate. Then you go further out, and at that time, if you think about the whole system closer and higher temperature and earlier, then you go further away. The reason of mineralization is in the proximal location, mineralization only occurs in the retrograde alteration, not in the high grade prograde alteration. That's because the temperature is too high. If you go to very further away place and even your first stage alteration is already low temperature, like the carbonate replacement environment and siderite and carbonate. And siderite then probably go to some place also have a little bit of dolomite. And by the time you have siderite, you can have mineralization together with the siderite, even in relatively early stage.
So is there a minimum of calcium oxide to have in a good host rock limestone?
It depends. If you look at our publication on Tamina in this year, 2020, Economic Geology, we talk about the ways of the combination of different inoskarn versus exoskarn, and a side effect or a side conclusion about that was that the skarns actually aluminum content always have higher than about 10.5%, and below that you form hornfels, and so that's the control of aluminum. But in your question will be, that's something I'm thinking about as a research project to continue to dig more into this, is the calcium. Again, if your calcium is low or aluminum content is high, and you end up as you produce a calcitic hornfels, and that happens in the early thermal metamorphic stage. So that's even before the water comes out of the magma chamber. And once you form that combination, then it's very difficult for that to continue to react to form hydrothermal skarns. So it should be a content control. I think aluminum, we are starting to see that. Calcium, we haven't worked on that yet, but it should have a less than certain amount of calcium. That means you're looking at a calcareous shale or calcareous siltstone. and you will end up as a carboxylic hornfels and not hydrothermal skarns. And if it is even less, then if you don't have any calcite at all, then bugger all, you won't have any skarns, not any types of skarns. Or if your calcium is in sandstones, in feldspar, not in calcite, and that's again no hope. You won't have any skarns.
So there's a question about permeability, and if the major influence of dirty limestone is to form good skarns, can a clean limestone with a secondary permeability also form major skarns?
Yes, yeah. If you have a shallow place, you're in the formation depths or the in-placement depths of that intrusion is shallow, then the limestone can break up a lot with lots of brittle fractures, and that helps channel the fluid flow, and you can also have large skarns.
We actually have a question about the graduate program, the offering. You wanted to go into a little more detail about that, what you're looking for, what people can expect from it?
So the courses will have geochemical exploration, geophysical exploration, geological modeling, and actually include a course, skarn and related deposits. We have 2 weeks, half day each day, about 12 days talking about, or are talking about skarns. We will have a very detailed understanding of skarn deposit and related deposits, and deposit models, and also management of exploration projects site. So the courses are more designed towards an industry career to help, after you finish, help you to be more successful in exploration, and hopefully advancing in your in position in your company.
Can you comment on pyrite zonation in an oxidized magma system?
Sorry, just back up a little bit. One more information is our most of our master degree program has been made into a block model mode. So if some of you may have heard about the block mode master courses in Australia, we are trying to convert to that model too. The only difficulty we have now is visa. Australia visa is relatively easy, and America is difficult. So the block mode would definitely be, if you are staying in the United States, probably Canada, you can do block mode and you don't need to leave your shop. You can just come for 12 days or 2 weeks to finish one course, then you go back, and after you finish your 30 courses, 10 courses, you got your degree. Yeah. Okay. Sorry about this.
Nope, it's great. The question dealt with, can you talk about the pyrite zonation in an oxidized magma system?
Pyrite zonation. You're talking about pyrite, because pyrite itself, inside its grain, you can have very delicate zonings. And one thing is you do etching. You do use concentrated nitric acid, and you put one droplet on your slide and wait for 15 seconds, wipe it off, and you will see the internal zonation of lots of pyrite. I don't see that scale versus very large scale donation. It may help you to understand some of the processes, but so far I haven't seen much of a particular usage in terms of zoning or vectoring of the detailed zoning pattern of the internal texture zoning of pyrite. And watch out is, yes, you mentioned pyrite oxide system, because in reduced system, you're getting a lot of pyrrhotite, you won't have much pyrite. And so pyrite is mostly in the oxide system.
So just a clarification, iron-rich volcano sediment host rock has the potential to form iron, copper, gold, or iron, gold-rich skarns.
Sorry, can you repeat that again?
So the iron-rich volcano sediment host rock, what is it more likely to form? The iron, copper, gold, or just iron, gold-rich skarns?
There's one example actually is Tangan in Ivory Coast in Western Africa. It's replacing basaltic andesite, and it's a gold skarn, and not much iron, not much copper. It's just a gold skarn. And other examples of replacing volcanic rocks is we have lots of iron deposits, no copper, no gold, and there's tin skarns and one molly skarn replacing volcanic rocks, mafic volcanic rocks. I haven't seen much copper, no.
Oh, and one more question about the master's. Is it offline, or can you do the courses online?
We are developing the management course into online, but others, I believe as a geologist, you probably want to see the rocks, and we have lots of good rocks from all over the world. And on all the public courses, we have lots of practice or labs on rocks and field trips, and also geochemical exploration. We have field trip and do also lots of different ways of sampling. It all requires field work and sometimes lab work. We are not planning to go online because we value the field skills of those courses.
We have several more great questions, but I think at this point we should end the discussion, and then I can share the list of questions with you, Zhaoshan, and perhaps you can follow up. And I want to thank everyone for joining us today for this presentation. And if you have additional questions, here is Zhaoshan's email address just one more time. And it will be on the SEG website as well. So you can reach him that way. And then I think I have one more slide. We have a couple more webinars scheduled. The information will be posted on the SEG website next week, but you can mark your calendars now and look for them. And with that, we have a survey that'll pop up after you exit the webinar. And I just wanted to say thanks again for everyone for joining us. And Zhaoshan, thank you for such a great presentation.
Yeah, thank you for organizing this, and thanks to everyone for listening, and still about 160 people are still online. Yeah, thank you for your patience.
Great. Goodbye.
Bye-bye.